All right, everybody. So welcome to the notes on motion equations. Just so you're aware, this is your homework. This is just watching this video. So you don't have to do anything. We will do a lot of practice problems in class. So just watch this video, pause as needed, and make sure you write down any questions so you can ask them in class. All right, let's get going. Okay, so far we've been dealing with all these different graphs for position time graphs, and for position, just as a reminder, we'll be using D for displacement a lot of the time. Position, displacement, it all means the same thing. Velocity, remember velocity, that's your displacement over time. Acceleration, remember that's your change in velocity over time, and obviously time. Now that what we're doing now, because we've been doing graphs for a while and relating all those things via graphs, but we can actually do this via just numbers and calculations. So if you have any number of these things, typically if you have three of them, you can always find anything else that you need. And I'll just let you appreciate this meme on the right side here. Too many physics majors would be doing this meme. All right. So here, I have this kind of broken down now, not into just position, velocity, time, acceleration, but we have initial position versus final position, right? We call this, that's our displacement, is our change in our position. That's our displacement. Truly, we'll be using the D as opposed to the X. But on the AP test, you'll see this delta X. You'll see this notation of X final and of X initial. You'll see that notation. Just remember, we will be using this as D because it makes the equations just a little bit easier to use. All right, initial velocity and final velocity. This is how fast something is going at the beginning and how fast something is going at the end. All right, time, initial time and final time. Well, truly what we're going to do is just take T as time. It's just the change in time. It's whatever has elapsed from beginning to end. As a little side note on this, you'll see this sub-zero. That means not. Like if I say x naught, that means x n-a-u-t. This n-a-u-t. Oh, sorry, that's the modern spelling. G-h-t. That means x at time of zero is why it's x sub-zero. Same thing with v. Same thing with t. So I'll say that as like v naught, x naught, whatever it is. All right. Anytime. Okay, so here's the 7 things that we could possibly have. Anytime we know 3 of them, we know everything else. And when I say that, I mean really, I'm going to count these two. These two goes as one variable. So these two, that's our displacement. These two also, that's our time. That's our time as well. So truly, there's 5. All right, you got me. There's 5. So V naught, V final, displacement, time, and acceleration. Those are our 5 variables we are really working with. So let's get into it a little bit more. Okay, here's our motion equation. So these ones on the bottom right, you can find on your equation sheet. Remember, your equation sheet is page 2 of every single workbook that we have. Page 2 of every workbook. And then on the left side here, this motion equations, these are what's underneath the general equations. The ones outlined in red are the ones that we're going to take a little extra time to look at specifically. Sorry, it's just a brief aside. I want to make sure the audio is working on this. So I'm going to come over and hopefully this is working. It doesn't show it, but I'm going to hope so. Heck. Oh, it's got a little record thing. Okay. I think it's going. I just don't know how to stop the recording. There we go. Okay. Sorry about that. Just want to make sure it's working. This is the second time I'm trying this, so bear with me. Thank you. All right. Oh, on this, I do want to point out those 5 variables that we had. Those 5 variables. Well, here's one. No, I'll use a different color. Here's one, V final, V initial, acceleration, time, displacement. If you look at the rest of these, all of the rest of these variables are one of those 5. Same thing over here, V final, V initial. Now we do we do have this V average over here. What V average truly is, it's the average between our initial velocity and our final velocity. So if you just take those, add them up, divide by 2, that gives us our V average. This V average really tells us that's our displacement over time, is V average. All right. So those are the 4 equations that we'll really be using. Those are the only 4 you ever need for motion equations. These other 2 over here, this is just, right, this is the definition of velocity. It's your displacement over time. And this is the definition of acceleration. It's your change in velocity over time. All right, anytime we use, or we do these motion equations, we are going to use this method, this guess and check method. So it's an acronym. It stands for givens, unknowns, equations, substitute, solve. And then finally, and this is the most important one, check for reasonableness. Does your answer kind of make sense? And as we go through the year, you'll get a better sense of what answers make sense, particularly for accelerations and velocities and whatnot. All right, let's try this. So an example, you begin a road trip home. It takes you 12 hours and 40 minutes to drive 623 miles. What is your average velocity in miles per hour? Okay. First part of this step, the G, givens. All right, so let's just write down our givens. Well, it takes you 12 hours and 40 minutes. So that's our time. So 12 hours, 40 minutes. Well, we don't really like breaking it down into hours and minutes, do we? We're going for hours just as a general whole. So let's do this 12.67 hours, all right? Because 40 out of 60. Okay, and then to drive 623 miles. Okay, so that's how far we went, 623 miles. All right, those are givens. What is our average velocity in miles per hour? So that's our unknown, what it's asking for. Unknown average velocity, so V average. And the way I'll do this, just equals question mark. All right. What is our average velocity miles per hour? Okay, so G, U, next one, E, equation. What we do here is we want to see, okay, let's take all of the variables that we have. So time, displacement, and V average. What equation do we have that we've been given over here, or actually over here? What equation do we have that relates V, time, and D? Well, this is going to be this one over here. So it's our average velocity, right, is our displacement over time. This is really, it's truly just the definition of velocity. So V equals displacement over time. You always, always, always have to write your equation with variables. The AP test actually grades you on this. You get a point for writing your equation. That's a point that everyone should get. Yes, it's a little extra work, but yes, you should do it every single time. You have to. I will grade you that way on your test this year. AP will grade you that way on the test in the end of the year. All right, substitute. So this is where we just put everything that we know. So our displacement, we substitute in the number 623 miles. Time, well, it took us 12.67 hours. So we just put that down there. So this was in miles, this was in hours. All right, and then solve. That's our last S. So if we come over to the calculator here, I'll just clear it all out. We just plug these numbers in. So 623 miles divided by 12.67 hours, 49.171, all those numbers. So how many sig figs do we like? 3. So 49.2. All right, so V average equals 49.2, and this was in units of miles per hour. Notice that's not a slashy fraction. Remember, no slashy fractions. All right, 49.2 miles per hour. Okay, last step. Our last step is this check for reasonableness. So is it reasonable? Well, all right, highway speeds, that's like 55 to 60 miles per hour. So averaging highway speeds if you're on a road trip, and then stopping, because if you're going 12 hours, I really hope you're stopping. I have a not funny story, but a relevant story to this at some point, but I won't bore you with it on the video notes. But between averaging the highway and stopping, yeah, 49.2 sounds pretty good. So I'll give that that's my little check to say, okay, looks good. All right. Oh, I forgot I typed these all out. Okay, so we can just click through all those. Awesome. Slide 13. Okay. A ball is thrown upward into the air with an initial velocity of 12.7 meters per second. It was thrown from an initial height of 2.50 meters off the ground. After 3 seconds, how high is the ball off the ground? Okay, as a quick note on this problem, it gives us initial position and it's asking for how high is the ball. So that's really final position. So this is really like x naught and x final. The way we're going to combine these just to make this easier on ourselves is with this d variable. So d is x final minus x naught. So I'm going to solve for displacement and just put this in a box for myself. All right, remember we start 2.50 meters off the ground. So whatever number we get, make sure we add 2.5 meters to it, and that's how high it'll be. All right, so let's go through our process here. So givens. The givens of this, well, I just read through the problem. Thrown upward in the air, initial velocity 12.7. Okay, 12.7 meters per second. Oh, I need to write what that is. It doesn't help me if I don't know what that is. So 12.7 meters per second, that is our initial velocity. All right, thrown from an initial height of 2.50 meters, right? We said we'll come back to that. After 3 seconds, so time 3.00 seconds, how high is the ball off the ground? All right, so there's our givens there. Our unknowns, we're looking for how high is the ball off the ground, so that's d equals question mark, our displacement. Okay, now if you remember what I said earlier, we just look for all of these variables and see, is there an equation that relates all of those? In this case, no. In this case, there is no equation that relates all of those. However, there's a hidden given. So I'm going to move this down to make room for our hidden given. Well, unless to say otherwise, what planet does this occur on? Well, it's Earth. And on Earth, right, acceleration of gravity is always 10 meters per second squared down. Now, it's important to say down because, right, if we're dealing with, we just get to decide whether we want to call up positive or down positive. Well, we throw something up, so let's call up positive. So that means that since this is down, this has to be negative 10 meters per second squared. All right, so our acceleration due to gravity, negative 10 meters per second squared. All right, so now, oh goodness sakes, now we have our fourth variable. Okay, so we have V naught, T, A, and D. If you take a look at our equation sheet, it is going to be this one. That equation uses all four of those. So as a reminder, you always have to write down the equation. Even though it's given to you, you have to write it down. D equals V naught plus 1/2 AT squared. All right. I can't tell you how many people in the previous years have not written down the equation and not gotten on a test, like they missed out on an A by a couple of points, which means on the AP test, you missed out by a 4 or a 3 even. You missed out on passing it by not writing down your equations. It is the easiest way to get your points, I guarantee you. All right, so now let's substitute. So we're still looking for displacements. That stays as D. V naught, well, it's 12.7. Time happens for 3 seconds. Okay, plus 1/2 AT squared. 1/2 acceleration, negative 10. Remember, it's downward, time 3 squared. All right. And then our last S solve. So D equals, where'd my calculator go? There it is. Okay, so on our calculator, I'll clear that out. So 12.7 times 3. Okay, that gives me 38.1. 38.1, and then plus 1/2, so 0.5 times negative 10 times 3 squared. 3 squared is 9, negative 45. All right, so negative 45. Okay, so our displacement, 38.1 plus negative, so minus 45, negative 6.9. And this is displacement, so that is in meters. All right, here's where we have to remember we did not start on the ground. So we started 2.5 meters above the ground, so our true final height, 2.50 meters minus 6.9 meters. That gives us 2.5 minus 6.9, negative 4.4. Okay, so negative 4.4 meters. There's our answer. And just to do a little check for reasonableness, well, we'll discover this throughout the year. Yes, it's negative. Okay, so that just means we threw it off the side of the cliff and the ball ends up below us. Okay, well, letting something fly for 3 seconds, that sounds about right. 3 seconds is a long time to be in the air. Really, anything that's within like 20 to 30 meters of you for throwing a ball up that's pretty reasonable. All right. A cart accelerates as it rolls down a hill starting from rest. If it takes 6.42 seconds to reach a final velocity of 8.3 meters per second, what's its acceleration down the hill? All right, Givens. Time, 6.42 seconds. 6.42 seconds. Final velocity of 8.3. All right, V final equals 8.3 meters per second. All right, unknown, that's our acceleration. What is the acceleration? Okay, do we have an equation that relates these three things? Well, remember what I said. You typically need 3 to find the fourth. Here's our hidden given here, starting from rest. So it starts from rest. So starting means at our initial time, and from rest means velocity is 0. So our initial velocity is 0 meters per second. That gives us our fourth. All right, so looking at those 4 variables, try to find an equation that relates those 4. It is V final equals V initial, or V naught, plus A T. All right, next up, substitute. So V final, 8.3. V initial, 0, plus A, well, A is what we're looking for, times T, 6.42 seconds. All right, all we have to do is solve. So solve 8.3. I'm just going to rearrange this a little bit. We can get rid of the 0, 6.42 times acceleration. And this, I meant to not put an equal sign there. That's just our letter for solve. Okay, so divide both sides. Divide both sides by 6.42. Divide by 6.42 leaves us with acceleration is equal to, okay, 8.3 divided by 6.42, 1.29. All right, 1.29 is acceleration, so units of meters per second squared. All right. Is this reasonable, right? Our last piece of this is our check. Is it reasonable? Well, right, things can only go downhill at maximum of acceleration of gravity, so 10 meters per second squared. This is significantly less, but it's going down a hill, so that kind of makes sense. As long as it's still moving downward, which it is, and it's not any faster than gravity, I'll call that pretty reasonable. All right, nice. Okay, I do want to bring up for the moment, though, that there's typically more than one way to solve any of these. Anytime you're given 3 of these variables, there's more than one way to solve it. So let's take a look at an example of this. I'll do it one way. My challenge to you is try to find a different way to do it. So when we're done with this problem, pause and try to find a different way to do this problem and practice it. All right, so while skydiving, a daredevil chipmunk accelerates constantly from rest. Ooh, from rest. From rest. Anytime you see those words, star it, box it, because what does that mean? V naught equals 0. All right, from rest until he reaches terminal velocity. During this time of 2.78 seconds, okay, time 2.78 seconds, he falls 19.46 meters. Okay, so displacement 19.46 meters. What is the chipmunk's terminal velocity? Okay, so this one is a little less clear, but terminal velocity, right? Our chipmunk starts out by falling, or it starts out at rest and then falls a little bit, and then falls a little bit more, and then falls a little bit more, and then falls a little bit more until he reaches this terminal velocity, some 19.46 meters farther down. That means that we are looking for his final velocity just for this little piece of time that we're interested in. We're looking for his final velocity, so the one down there. So our unknown is V final. Okay, so there's our four. Well, we've got V naught, we've got time, we've got displacement, we've got V final. This one, it doesn't truly show up over here. You have to really use the definition of velocity and combine it with velocity average. However, we have a fourth given, actually. So we have a fourth given, right? Because what planet do chipmunks live on? Last I heard, they live on Earth. So 10 meters per second squared. All right. Here's my question, though. Why did I call this 10 instead of negative 10? Well, it's our distance. I said our distance was positive, right? But the distance was down because as the chipmunk is falling down, that's a positive distance is what I called it. Okay, so in this case, down, for this problem only, down equals positive. Down equals positive. Okay, so that's why acceleration is just 10 in this case. All right, so unknown. Let's find our equation, though. So our equation, well, now that we have acceleration, well, we have V final, V initial, A and D. Okay, we could use that one. We could use this one. We could use this one. As I mentioned before, we could use that one. So actually, we can use any of these. So truly, my determining factor is which one is the easiest. If you can use this one, it's the easiest. So V final equals V naught plus AT. That's our equation. So when we substitute, that's V final is equal to, right, 0 plus 10 times the time of 2.78 seconds. So when we solve this, this just turns into V final is 27.8 meters per second. All right, and I'll just tell you right now, 27.8 meters per second, right? It's about 55 miles per hour, right? It's just about double. So yeah, that makes about sense for a chipmunk just falling through the air. All right, one last problem. I'll do this one kind of quickly. Okay, tennis ball hit straight up. Initial velocity of 32.4 meters per second. Okay, V naught, 32.4 meters per second. Oh, okay, so we're back to hit straight into the air. We're back to up equals positive for this problem. The up direction is positive. All right, how many meters above the ground did the tennis ball go? How many meters above the ground did the tennis ball go? So we're interested in how high up did it go? What was its maximum height above the ground, right? Because it goes up and then it just sits there for a moment and then it comes back down. We're interested in this height. Okay, there's our height, but it starts from 1 meter above the ground, so we have to make sure we remember that 1.0 meters above the ground. Same thing that we did earlier. I'm going to box it and come back to it later. But we are interested in displacement. All right, two hidden variables though in this case, right? What planet does tennis take place on? Earth. I have to do negative 10 meters per second squared again here because we said up is equal to positive. So now our acceleration of gravity goes back negative. And then here's the fun piece because we're looking on the way up. So we're looking at this ball as it's traveling up. But when it hits this top here, when it hits the top for just a moment, it is stopped. 0 meters per second, it is stopped. So if we just call the moment on the way up as what we're interested in, then that means that this here up at the top, we can call that the V final. All right. So now we have 1, 2, 3, 4 variables. We can find this. So our equation, if you want to pause, try to find the equation, what it is here. But I will tell you now, V final squared minus V naught squared equals 2AD. All right, substitute. When we substitute V final squared, so 0 squared minus and 32.4 squared equals 2 times acceleration of gravity. Remember, negative 10 times d, that's what we're looking for. Okay, and solve. Well, the 0 squared just kind of goes away. So negative 32.4 squared. All right, so remember we do 3 sig figs, so 1050 is what we'll round that to. So minus 1050 is equal to, okay, negative 2 times 10 is 20 d. All right, negative on both sides, get rid of it. Divide both sides by 20. So 1050, 1050 divided by 20, 52.5. All right, so our displacement, 52.5 displacement, so meters. Okay, but here's where we have to remember our little final piece. Final piece, started 1 meter above the ground, so that means it's maximum height above the ground. I'll just say H max, maximum height. All right, we just add 1 meter to that, 53.5 meters. As far as reasonableness goes, yep, I'm going to say it's pretty reasonable. It's about 150 feet. So it takes a strong tennis player, but definitely doable. All right, let me know if you have any questions. Please bring them into class. But otherwise, thanks for sticking around, and I will see you in class.